Hi, how are you doing? Welcome to our technology refresher class. And like I say, and this is a really kind of a basic fundamental approach to technology, just a little refresh, but I tried to approach this from a cybersecurity perspective, not so much from an IT perspective, but we'll get into both. Now, where are we at in the course? Like I said, we're still in module 1. We finished part 1, we finished part 2, and yes, we're here at part 3. So let's get this going. Some of the things we're going to cover: computer hardware, operating systems, virtualization, the OS model. Yes, that OS model that everybody loves, and protocols. And then we'll go through some networking. So let's look at some computer concepts. Basic computer processes. When you think about computing in any environment, really you start with an input. Like I said, that's where you're going to get your data. That's where you're using your keyboard, your mouse. It could be webcams, a lot of interfaces now. That's how you're going to get some type of input into your system. And then at the processing, something has to be done with that information, that data once it comes in. And that's where your central processing unit comes into play. Then from there, it's been processed. Now it's an output, right? Now that's going to, we send that. It could either be crossed to a printer, to our monitor, or to some networking device as well. And storage, because we also need to be able to store information in a basic computer process. And that could be hard drives, optical media, it could be flash drives, many different things to look at. But input, processing, output, and storage. So now let's take a look at a basic, here again, basic computer design, okay? So really we always start at the bottom layer when we talk about basic computer design with computer hardware. That's your central processing unit, storage, memory, all of those things, that hardware. Now on top of that hardware, that's where we will place an operating system. That operating system could be a Windows system, it could be Linux, it could be a Mac OS, just depending on what type of operating system. But that operating system sits on top of that hardware. And then on top of our operating system, that is where our applications. And so you see we have a hierarchical or a structured approach to how our computer design is put together. And it's put together that way for security reasons, because there are very few things that computer applications can go directly to hardware. Everything needs to be vetted through an operating system. So that gives us a layer of security. That gives us some type of security protection to protect our computer hardware and some of the critical components within our operating system from malicious users. And talking about users, that's where we sit. And we interface with those applications via the operating system that is sitting on top of hardware. So that's that basic computer design. Okay, now when we take this, we're gonna drill a little deeper into each of these components, right? So let's take a look at some of the hardware. At the heart of our computing system really is the central processing unit. That's CPU. CPU has 3 basic components to it. It has a control unit, it has a arithmetic logic unit, and it has memory. Okay, and within these three areas, that's where the core basic part of computing takes place. It's in our CLU. That's where we have the fetch, decode, execute, and store. Now, really, we think computers are really smart. Really, they're not, because really this thing can really only do one thing at a time. It's really a very high powered adding machine. It just does arithmetic logic functions: add, subtract, multiply, and divide. Actually, it really just does addition, because if you think about it, that is really the only mathematic function that you really have. Not that I'm a math major, but what is subtraction? That's what? Negative addition. What is multiplication? That is addition over and over and over and again. And division, that is where we're doing negative addition over and over. So really, this thing can only add ones and zeros. We call them ones and zeros, which is our programming code is made of. So what does it have to do? It has to fetch. Right, one of the things that's where it starts. So it has to be able to get program instructions from the computer's memory. It has to be able to bring that memory in. Then decode. What is decode? That's when it looks at that program instruction and it says this is what the computer wants to be able to do. So it has to tell the computer what to do based on that program code. Then the execution phase, that's where it processes that requested action. And here again, these are just all, a series of ones and zeros, all binary execution that we're doing. And store, then it writes the result of that either to a register or to memory. And speaking of that, that is what our memory section is. That's what three kind of basic types of memory we would look at when we're talking about that CPU and that motherboard function. We got registers. And what a register, and you may hear these terms and always wonder, well, what's the differences between these? Well, what a register, this is what holds the data that your CPU is currently processing. Okay, these are really relatively small memory locations that's sitting right here on that chip. That's that CPU chip on the motherboard. This whole thing is the motherboard, and that's the CPU. So right there on that CPU, you have registers that's holding the program code that CPU is currently processing. Now cache, that's really high speed memory that's located very close to the CPU. Sometimes you may have it on the CPU itself, and sometimes it's located really close on the motherboard. Three levels of cache: level 1, level 2, level 3. Level 1 is the fastest, level 2, and then level 3 is the slowest. So and the reason we have cache. Okay, this CPU is operating at really, really high speeds, up in the gigabits. If you look at the rest of our memory, many times it's operating, at the megabit range. So our memory is much slower than our CPU. So this cache memory, which is really high speed, it's able to feed things into that CPU a lot quicker and a lot more efficiently than if we were trying to take it straight from RAM, or worst case than that, straight from our hard drive. So that's why. It's kind of like our brain. Our brain processes information much faster than our ears can hear it or even our eyes can see it. That's why many times when we're in class lectures, we get bored because the instructor is speaking in a very monotone and very slowly, and our brain is like, come on, give me that information. And we're only hearing it so fast. And then our brain starts looking for other things to do. Oh, look at that, squirrel. So that's why we get pulled off. So CPU works the same way. It is processing much faster than these input sources. And then we have our regular memory. The memory, that's what holds your program instructions and data that's waiting to be executed. So you see there's a process. Now, trust me, understanding a CPU is an entire course all its own. So for the purpose of this refresher, this is about as deep as we're going to go into the CPU. Okay. Now let's take a look at memory. Something that I always like to say, this is memory and not storage. Sometimes we get these two, we use them synonymously, memory and storage, two different things. Okay. Memory, we're talking volatile memory, like RAM. It could be DRAM, dynamic random access memory, RAM. That's a chip that has to be refreshed periodically or it loses its data. So when we look at memory, it is not storage, okay? We're going to talk about storage a little bit later. So this is our volatile memory that actually hold with it, that when we bring things from storage, it holds it in the computer. Now, the thing to remember, when we turn the power off, anything in RAM is lost, okay? So anything in memory, whether it's in cache, whether it's in a register, or whether it's in memory, all of that is lost when we turn the power off. Different types of memory or RAM you may see. One is SDRAM. Okay, if you go into Newegg or you go into Best Buy or whatever your computer store near you, and you see all these different. What does all this stuff mean? SRAM and SDRAM and DRAM and DDR. Oh my God, I'm confused. Not that difficult. SDRAM, like I say, DRAM is dynamic random access memory. SDRAM is synchronous dynamic random access memory. What basically means, it is synchronized with your computer's clock. So basically, on every clock cycle, think of that as a cycle, things are being either read into or written into your RAM. Okay. Now later on, they say, hey, we can speed this process up. So they did double data rate, DDR. That's what that stands for. Double data rate SRAM. Now, what that is able to do is able to send and receive data on a clock cycle. Here, I can send on one clock cycle. I can receive on another clock cycle. Here, I can send and receive on a clock cycle. So you can imagine double data rate is just like it says. It doubles the data rate of your storage. Now let's look at, of your memory, I'm sorry. Now let's take a look at some different storage. We're very familiar, I'm sure, with storage. Our hard disk drives, whether it's flash memory, solid state drives. This is where information is stored at. It's not memory. This is permanent storage. Like I say, this is non-volatile. So meaning that I can turn the power off and the information, the data is still there. Now, this is by far one of the most important parts of your information of your computer system, okay? Because that's what we are protecting, is we're protecting the data. Companies have gone out of business because of losing data on hard drives. So understanding how to protect this information, many times now, what you'll see in organizations where we do things, or we full disk encrypt data on these types of drives. You know, when it was called data at rest. You may have BitLocker if you're a Windows person running on your computer. What does BitLocker do? Yeah, it encrypts everything on that hard drive. If you're a Mac OS person, you may have File Vault running. File Vault does the same thing. If you're a Linux user, you may have Lux running. That does that full disk encryption. Why? Because we want to be able to protect the data. Okay, so now let's bring these together. And so how do these pieces work together? And this is my computing analogy. And it's based on Ada's kitchen. Yes, Ada's kitchen. And Ada loves to cook. So here's Ada. And she's going to prepare for us today a salad, okay? A fresh garden salad. Now, in this analogy, in Ada's kitchen, she is the CPU. She is the one that's going to fetch, decode, execute, and store. She's going to perform those functions. So, when we look at her kitchen, she has a cutting board. And that cutting board really is analogous to cache, meaning that those are the vegetable components that's right there really close to her, so she can cut them really fast. That's what the cache is. Now we look at her countertop. Her countertop is like RAM, okay? This is where she can store things temporarily, and it's not as close to the CPU as cache. It's a little farther away, so this is where she can bring things out and set them down and cut them up. To prepare this delicious salad that she's making, okay? That's her RAM. Now, when we think about storage, that's the refrigerator. That's long-term storage. That's where all the vegetables and everything is kept, everything is in there. Now, if you notice, her countertop is pretty small. Now, anybody who loves to cook, and you talk to any person who loves to cook, and especially if they're buying a house, what's the first thing they're going to do? They're going to go to that kitchen and they want to see how much countertop space do you have. Cabinets and countertops, right? Because they know the more countertop space you have, the more you can get done. So thanks to Aida's fabulous husband, who works really hard, he went out and he bought and redid her kitchen to where now she has a much larger countertop, meaning she has more RAM, just like your computer at home. If you don't have enough RAM, random access memory, then your CPU is kind of constantly having to go to the refrigerator, bring something out, go back to the refrigerator and bring something else out, take this back to the, so you see that there's a lot of work going on just doing a fetch to get things from storage back and forth. Well, now that she has this beautiful redone, remodeled kitchen with a lot of countertop space, she's able to bring a lot of stuff out at one time. Boom. Look at it. She's got onions. She's got lettuce. She's got cheese. She's got tomatoes, as well as the cucumber she was already cutting, all now sitting out here. And right there where she can easily get to it, chop it up. So that's how this process works. CPU, cache, RAM, additional RAM if you need it, always recommend it, and storage. Now she makes this delicious salad, and where does it go when she finishes with it? Because she's not ready to eat it or serve it just yet. So it goes back to storage, puts it back in that refrigerator. The same thing we do when we're in a computer environment. When we finish with a document, where does it go? It goes back and is saved or stored on our hard drive. Our kitchen, Ada's kitchen computing analogy. Hope that helped you kind of bring all those pieces together. Okay, we're going to take a break here. We're going to come back, talk about operating systems and virtualization.